So the given data is R134A is the type of the substance. Pressure is 1 megapascal and temperature is 50 degrees Celsius or 323 Kelvin. So at this pressure and at this temperature, this is a gas. This must be a gas because we are using ideal gas equation. So it must be a gas, but you can check it with the help of saturated table whether at this pressure and temperature this refrigerant is a gas or not. We have learned in the steam table portion that for a given temperature and pressure, how to find out whether a substance is in superheated region or mixture region or in the subcooled region. Here we are discussing the topic of a gas, so this will be a gas, but to be sure you can check it with the help of saturated tables whether it is a gas or not. Okay, so at this pressure and at this temperature we need to find out the specific volume, and actual or real specific volume is this one. So this is V actual. Now we will calculate the part A, the using ideal gas equation, the same specific volume using ideal gas equation. And table A1 at the end of this book, from there we can find out this constants are in the gas constant for this refrigerant. It is 0.0815 kilopascals meter cubes per kilogram per Kelvin. Critical point data P critical and T critical for this refrigerant. So table A1 at the end of this book. Now for part A, we need to calculate specific volume using ideal gas equation. V is equal to RT over P specific volume. That's why there is no M. Now by putting values, R is this one, gas constant. Temperature is 323 Kelvin. Temperature will always be in Kelvin divided by pressure because here in the units of R is kilopascal meter cube, so this pressure must be in kilopascal also, so you convert this megapascal into kilopascal. So now all the units are same. All right, so now this kilopascal will cancel with this kilopascal. Kilogram will stay there. Kelvin will cancel with this Kelvin, so the answer will be in meter cubes per kilogram. So the volume comes out to be 0.026325. Right. So now this is the volume which we have calculated using ideal gas equation, and this is the real volume. So now the percentage error, both are not same. In the third decimal there is a big difference, and this is 0.021, this is 0.026 meter cubes per kilogram. So let's calculate the percentage error between these two values. So how to calculate the error? V, which we have calculated, which is this one, minus V actual, this one, divided by V actual multiplied by 100. Right. So by putting the value, so the error calculated to be 20.8%. So if we use PV is equal to RT, ideal gas equation, to calculate this specific volume, and then the error with respect to the real or experimental value is 20.8%, so which is quite large. So it means we should not use PV is equal to RT for this gas at this pressure and temperature. Now we shall calculate the specific volume using PV is equal to ZRT, the second part, using compressibility chart. Now you will understand the meaning of compressibility chart, why we have learned this chart, how to use this chart in the numerical problems. So from compressibility chart we need to we have seen that this compressibility chart had two axes. One was Z y-axis and the second was PR. This compressibility chart has two axes. On y-axis we had Z values, on x-axis there were reduced pressure values and a number of such curves for different PRs. So to find out Z, first we need to calculate PR and TR, the intersection of this PR and TR somewhere that intersection will give us the Z value. And then we can find out PV is equal to ZRT equation to calculate specific volume. So first we need to calculate Z because PV is not equal to RT. And how Z can be calculated? For Z we need to know what is PR and TR. So let's define PR and TR. And what is PR? PR is defined as P over P critical. Critical point data is available, should be known, it is given for that refrigerant which we have seen in the last slide. So just put the values. Given pressure is 1 megapascal, critical point pressure is 4.05, 9 megapascal, so PR is 0.249. Similarly, TR, T over T critical, given temperature is 50 degrees Celsius or 323 Kelvin divided by T critical, and it comes out to be 0.863. So now we shall go to the chart of Z chart, and for this PR and for this TR, we shall find out Z value. So let's go to the chart. So here is the compressibility chart on where we have Z values versus PR values. This chart is taken from this book, Shapiro's book, because the chart which is available in the Cengel book is not easy to read. The values are too small to be shown on the slide, so that's why I have used that chart from this book. So now here the PR we have calculated, it is 0.246, and PR line, because PR is x-axis, so PR lines are vertical lines. So now we have to trace the vertical line of 0.246. This is 0.2, this is 0.25, this is 0.3, so 0.246 will be somewhere here. So draw a vertical line of 0.246. This is the vertical line. The second is TR. So these are the TR lines. All these are TR lines, and these are VR lines, so, reduced volume lines, which we will study later on. These dotted lines, these solid lines in this direction, these are TR lines. So what is TR value? 0.863. So this is 0.8, this is 0.85, 0.9, 0.95 TR lines. So all these are TR lines. So our desired line is 0.863. So this is 0.8, 0.85, and this is 0.9. So 0.863 will be somewhere here between 0.85 and 0.90 line. So you can imagine there will be 0.86, 87, 88, 89 and 0.9. So 86 is somewhere here. So there you can imagine an intersection of this PR and TR of 0.863. So for example, this intersection is somewhere here. There will be this line, imaginary line, 0.86, and here is the intersection. So from this intersection, now we have the intersection of PR and TR. To read Z value, we shall draw a vertical line, sorry, horizontal line, because Z lines are horizontal on this chart. So here is the horizontal line, and now we can read Z value corresponding to PR of 0.46 and TR of 0.863, which gave us this intersection point. From that intersection point, we have drawn a horizontal line. So now you can read the Z value. It is about 0.85 or a little lower than 0.85. So in the book, the value is 0.84. There will be some reading error. So that is fine. Point in the second or third decimal, the error is acceptable, but not more than this one. Okay, so now Z is calculated with the help of this compressibility chart. So that is the purpose of that compressibility chart, and you can see this value is not 1, is not near to 1, it is away from 1. That's why PV is not equal to RT. PV is equal to Z RT, and the value of Z is not 1, it is less than 1. So that's why this substance is not behaving like an ideal gas. When we used ideal gas equation, the there was an error of about 20%, but now this error should reduce because now we have calculated Z value. So now let's go back. So we were here. Okay. Now from compressibility chart for PR of 0.246 and PR of 0.863, we have calculated Z factor, which is 0.84. Now we can calculate V using PV is equal to ZRT, where Z is now estimated 0.84. Or in other words, V is equal to Z into V ideal, which we have already discussed. So either use this equation or use this equation to find out V, where V ideal is RT over P, which we have already calculated. In the part A, RT over P was B ideal, which we calculated 0.26325 into, now the Z is 0.84. Now volume is 0.22113. So using compressibility chart, we have now calculated specific volume. Now we can find out the percentage error, because now we can compare this V with this real V, right? So now if you calculate the percentage error, we calculated this one minus V actual, this one divided by V actual, right? So in the denominator, we shall write the term which is the standard with which we are doing comparison. So to memorize whether it should be V calculated minus V actual divided by V actual, or V calculated, so it should be V actual. Why V actual? Because we are comparing with this value. So this is the standard or reference value, so that value will come into the denominator. So after putting all those values, error is now only 1.45%. So now using compressibility chart, we have reduced this error to 1.45% because ideal gas equation was giving us a wrong result. But we can use the same ideal gas equation by the introduction of that compressibility factor, which is Z. Right. So now in this problem, pressure and temperature were given and volume was unknown. That's why we have used PR and PR to find out Z and then V. There could be problems where pressure and volume are given and temperature is unknown, or temperature and volume are given and pressure is unknown. So in that case, we need to define VR also, because then we will try to estimate Z with the help of PR and VR to calculate T, right? So now we have to introduce one more property, which is VR. So just like PR and PR, VR is equal to V actual over V critical. But here V critical is calculated from this ideal gas equation, or T critical over P critical. Normally in the case of reduced pressure and reduced temperature, in the case of PR, this was calculated by dividing P with P critical, and we see this P critical from table. Similarly for TR, this was T critical, and we can see these values from the table, the P critical and also T critical. But for V critical, it is better to use this equation, or T critical over P critical is actually V critical. What is the reason? So the reason is not easy to explain here in this recorded lecture, so I will explain it in the face-to-face or on campus class. Why we are not using P critical value from the table, right? So for the timing, just remember, for PR, P critical is from stand tables, and T critical in the case of TR is also from table, but in the case of VR, V critical is calculated using R, T critical, P critical. R is the gas constant, T critical and P critical are taken from the tables for their particular gas. Okay. So now we have introduced VR, and that ratio is also known as pseudo-reduced volume. This VR is also known as pseudo reduced volume. This was reduced pressure, similarly reduced temperature. This is specifically named as pseudo reduced volume. So now if PR is given, VR is given, now we can calculate Z using the same figure, but now PR and VR are given. TR is not, and TR may be unknown. Okay, so now we shall solve another problem where we will use VR also. So here in this question, a closed rigid tank. So a closed means no mass is entering or leaving. Rigid means volume is fixed. So there is a tank which is closed and rigid. Closed, no mass can enter or leave. Rigid means volume will not change. Volume will remain constant volume of this tank. So a closed rigid tank filled with water vapor, initially at 20 megapascal and 520 degrees Celsius. So we have, let me show it on diagram. For example, here is a tank, closed and rigid. In this tank, there is water vapors at pressure of 20 and 520 degrees Celsius is the temperature. Now it is cooled. Cooled means heat is taken out. When this water vapors will be cooled down, its volume should drop, right? And pressure should also change, right? But here it is written that it is a rigid tank. So rigid tank means the overall volume will be same, right? So it means volume will not change. Then when volume will not change, then it means pressure will change, pressure will drop, because volume is not changing, right? So the pressure will change. That is the main thing. Now when heat is taken out or when it is cooled, its temperature drops to a lower value. For example, take 400 degrees Celsius. This was the initial data. Pressure of 20 megapascal, temperature of 520 degrees Celsius. Now heat is taken out, but volume is kept fixed. Volume is not changing, and the mass is also not leaving the system. M is not crossing, so M cannot cross the system boundary during this process. So what is happening? Pressure will change. So we need to find out using the compressibility chart, determine the specific volume of the water vapor. Specific volume means meter cubes per kilogram at the initial state. Initial state is when temperature was 520 and pressure was 20 megapascal. The second part is to find out the pressure in megapascal at the final state. Final state means P2, because initial pressure is given 20 megapascal. The final pressure P2 is to be calculated in part B, and both of these parts we need to use compressibility chart to solve these two parts. So it means we will be using PV is equal to ZRT, right? And Z will be calculated from compressibility chart. Then we need to compare the results of this part A and part B with the values obtained from the superheated vapor table, right? So after calculating this volume, specific volume at initial state V1 and pressure at the final state P2, then we need to compare and check the error between these calculated values with the real values which are available in the superheated vapor table, right? So that is the question which we need to solve, because water is non-ideal gas, so that's why we are using compressibility chart. So this was the schematic diagram of this problem. This is a tank, closed and rigid. Initial initial temperature, final temperature. Cooling is being performed, and that's why, for example, this tank is placed on a block of ice. That's why it is being cooled from 520 to 400 degrees Celsius. Heat is leaving the system, and the system boundaries are shown here by dotted lines. Okay, so we need to part A is to find out the specific volume of the water vapor at the initial state V1 corresponding to P1 and P1. So now we have to use compressibility chart. It means PV is equal to ZRT. So to find out Z, first we need to find out TR initial state. So that's why TR1, T1 divided by TC, T critical. So we can see the critical point temperature from the table, and that is 647.3 Kelvin for water, or 273 degrees Celsius. But here everything is Kelvin by default because it involves a single T, not delta T. So T1 is 793 Kelvin, 520 degrees Celsius plus 273. That's why it is 793. So TR at state 1, reduced temperature is 1.23. Second, what is given? Pressure. So now we will calculate reduced pressure, P1 over P critical. So P over P critical. P critical for water is 22.09 megapascal, and given pressure is 20. So it is not far away from critical point data. That's why this PR is 0.91, near to 1. So that's why we must use compressibility chart. We shouldn't use PV is equal to RT or ideal gas equation. Now we can calculate V1, PV is equal to ZRT, or V1 is equal to Z1 RT1 over P1 at initial state. So first of all, we need to calculate Z1. Now what is given? TR1 and PR1 are already calculated. So using this TR and PR, we can find out Z from compressibility chart. So let's go to the compressibility chart. Here is the compressibility chart. Now what was, sorry. So PR1 1.23 and PR1 is 0.91. So here first we will draw the PR line 0.91, this one, and what is PR1 1.23. So this is PR line. Now 1.23, here you can see PR lines, these ones solid lines, 1.15, 1.20, 1.30. So 1.5 will be somewhere here. So 1.23 a little lower. So there will be, this will be the intersection of PR and TR somewhere here. And from here we shall draw a horizontal line to read Z value. So let's draw a horizontal line. So this is 1.2. So 1.23 will be somewhere here. And that is the intersection. So now we can read the Z value right from this diagram. So that is about 0.83, or yes, this is 0.8, 0.85, so it is about 0.83. So Z value is a 0.83 into R T1 over P1. Now R is the universal gas constant for water vapor. So universal gas constant for water vapor, sorry, the gas constant for water vapor, if you can see its value from table, but if it is not available or it is not given, then you can write this R as RU divided by M, which we have already discussed, where RU is the universal gas constant and M is the molar mass of the gas. So, and which value of RU, for example, we are using this one. and molar mass of water is 18.02 kilograms per kilomole. So we have replaced R with Ru divided by M. Universal gas constant, here are the values which you should remember, and that is 8.314, because pressure, if pressure is in kilopascals, volume is meter cubes, this is kilomole and Kelvin. So let's put values. 0.83 Z, R is written as Ru divided by M. Here we are using 8314 because 8314 means pressure is in pascals. This pressure should be in pascals, 20 into 10 to the power 6. If you write it in kilopascals, then it should be 8.314, right? Newton meter means joules, or kilojoules. If you transfer it to kilojoules, then it should be divided by 1000 and 8.314. But pressure is in pascals, so that's why it should be in joules per kilomole per Kelvin, divided by 18 kilograms per kilomole. Temperature is 793 Kelvin. So everything is now inserted. Now we can calculate volume V1. That comes out to be 0.015 meter cubes per kilogram. So that is the specific volume of water at the initial state. Second part is to find out the pressure in megapascals at the final state, P2. We need to calculate now P2. So for P2, what is given at final point? P2 is given and P2 is unknown. To calculate P2, we need to know T2 and also V2. With the help of V2 and T2, we can find out P2, pressure, at this point. But what about volume? Here volume is not given, so what is volume at point 2? We have seen, or we have already said that it is a rigid tank, so it means volume will not change. So when this water is cooled down, its volume, the overall volume, is not changing because it is in a fixed rigid tank whose volume is fixed. So that's why V2 will be equal to V1. So now for point 2, what is given, P2 is to be calculated, and it is a rigid vessel, that's why volume will not change, so V2 will be equal to V1. And V1 we have already calculated in part A. What else? So with the help of this, we can find out VR, V2 over V critical, and V critical we have to calculate using this equation, R P critical over P critical, or in other words, V2 into P critical divided by RT critical. So put the values of, by putting all these values, V1 is equal to V2, which is calculated in part A. P critical for water, you will see from the table. R can be written as Ru divided by M, or directly you can read its value from the table, otherwise universal gas constant divided by M into temperature. So pressure is in pascals, so that's why it is joules per kilogram per Kelvin. So the answer is 1.12. So V reduced volume, pseudo reduced volume is 1.12. Now we have calculated VR. Now next we need to calculate TR at state 2. So T2 over T critical. T2 is given as 400. So 400 plus 273, 673 divided by P critical for water, which is 1.04. So P2 over P critical. Now we will go to the table, the same chart, compressibility chart, because now TR and VR are known. Now the intersection of VR and TR will give a point, and we can read Z value or directly PR value. So let's go to the chart. So these were the lines for part A. Now for part B, what is given? For part B, TR is 1.04. So let's look at TR of 1.04. Here are the TR lines. So here is 1.95. This is TR of 1. TR of 1. This whole line represents TR of 1. And this line represents TR of 1.05. So 1.04 will be somewhere here, going like this one. So TR line is located Second is VR line. VR lines are these ones. These dotted lines are VR lines, and their values are written here. This is 0.7, 0.8 VR line, 0.9, and so on. All these are VR lines, reduced volume lines. So what is VR value? VR was 1.12. So we need to find out the intersection of TR of 1.04 and VR of 1.12. So here is the TR, VR of 1.12. Here is 1, this is 1.1. So 1.2 will be somewhere here. Let me show it. So this is VR of 1.1, this is VR of 1.2. So 1.15 will be somewhere here in the middle. So 1.12, okay, try to, so you will draw an imaginary VR of 1.12, a little higher than 1.10, but lower than 1.2. And second was TR line. TR, this is 1.05, and our TR, given TR is 1.04, like this. So this is the intersection, most probably. So this is VR line, and this is reduced temperature line, and here is the intersection, and from there you can draw a vertical line to read Z, or you can draw a vertical line. So this is the horizontal line to read Z value, and this is the vertical line to read reduced pressure or PR value. All right, so with the help of both of these we can find out P2. Let's go back. So now from the chart we have calculated PR, and PR is given as P over P critical, P at second state, P2 over P critical. So from here we can calculate P2. P2 is equal to PR reduced pressure, which we have seen from that table. This reduced pressure is about 0.69. So, or you can calculate P2 with the help of Z. You can use P2 V2 is equal to Z R P2. So we can calculate P2 from this equation by putting Z, or we can calculate P2 from this equation, because we know what is PR, which is this one. PR is given by P2, because we are at state 2, divided by P critical. So either use this equation or use this equation to find out unknown P2, because we have seen Z, which you can read from here, or PR from here. So either use this or use this to find out pressure at state. So we have calculated P2 is equal to PR2 into P critical. So here is the PR2 into P critical. So that comes out to be 15.24 megapascals. So now part A. In part A we have calculated V1 using compressibility chart. In part B we have calculated P2 pressure. That comes out to be 15.24 megapascal. Now we shall compare both of these values with the real experimental values from table, from superheated steam table. So let's now find out V1 from superheated steam table, which we have calculated using equation in part A. So let's go to the table. Here is that table. Here is the superheated steam table. So what we need to calculate, V1 at pressure of 20 megapascal and 520 degrees Celsius. So in that superheated steam table we need to locate these 2 points, 20 megapascal and 520 degrees Celsius. Here is the 20 megapascal, and these are for different temperatures. Temperature is 520, but 520 value is not given at 520. Values are available for 500 and 550. So here is the pressure, here are the temperatures. So we need to interpolate between these 2 points. Here we need to interpolate between these 2 points, right? Because pressure of 20 megapascal but temperature of 520, the value is missing. Here values are given for 500 degrees Celsius and for 550 degrees Celsius. So 520 is somewhere between these 2. So we need to interpolate. So for interpolation, we know this formula, which we have already seen in the previous lecture. So we have to use the interpolation formula to find out so y's are the unknown. What is the unknown? We want to find out specific volume at 520 degrees Celsius, but specific volume at 500 degrees Celsius is given, and specific volume at 550 degrees Celsius is given. So this is y0, this is y1, this is y0, and this is y, the unknown. And what is given? Temperatures. X are the temperatures. This is the temperature at which we want to find out V. This is the temperature at which we want to find out V. This is the temperature at which V is given, the previous value, and the forward value or the next value at which V is given, and this x0 corresponding to y0. So this is the only unknown. This value, specific volume at 500 degrees Celsius, you will write it from table at 500 and also 550. That was here. These 2 values. This one. At 500 V is this one. At 550 this is V1. Let's go back. So put those values. This is the only unknown. Right. So we now calculate V1 from table, the real value. And the V1 which we have calculated from compressibility chart, that was calculated as 0.0152 minus, this is the from steam table. Steam table values are the real or experimental values. So this is V actual divided by V actual. So this here is the error. Percentage error is only 1.93%. Right. Similarly, now we shall see for the case of pressure. For pressure, again from superheated steam table, we need to find out P2 for this temperature, P2, and V2, which is equal to V1, and that was 0.0152. So now we need to calculate P2 at P2 of 400 and pressure, volume of 0.152. For 0.2, what is given? P2 is given and V2 is given, which is equal to V1. Now instead of using compressibility chart, we are using steam tables, and that is in superheated steam table. So with the help of these 2, we need to find out P2. So let's go to the steam table again. Here is the steam table, and now V2 is given and also P2 is given. So what is V2? 0.0152, which was equal to V1, 0.0152, and P2 is 400 degrees Celsius. So where is P2 is 400 degrees Celsius, but there are many possibilities of pressures at 400 degrees Celsius. But now we need to look at V2. Where is V2? Now the given V is 0.0152. So V is, let me write here, V is 0.015, volume is given and temperature is given, and we want to calculate pressure 400. So yes, so volume is 0.152, temperature is 400. So now either this volume is not 0.152, this is greater than 0.152, this is lower than 0.152, and this is even lower than this one. These are the V values for different pressures, but for the same temperature of 400 degrees Celsius. 400 degrees Celsius temperature, but at this pressure this is V, at this pressure this is V for this 400, at this pressure this is V for the same 400, and our desired value is between these two, between 0.156 and 0.012. So it means we need to interpolate between these two pressures. So our desired pressure will be between these two pressures, temperature of 400, volume of 0.0152, which is between this and this volume. So our pressure will be between this 15 megapascal and 17.5 megapascal. So it means we need to interpolate between these two pressures for the known volume, because now volume is known. Pressure and temperature in both of these cases is same, 400, but volume here is different. So our volume is between these 2 points, so pressure will be between these 2 points. So let's do the interpolation for pressure and volume. So the same interpolation formula, but the unknown is pressure. This Y is pressure at volume of 0.0152, because we need to calculate pressure at this volume. And what is given? Pressure at this volume, 15 megapascal. Pressure at this pressure, the volume is 0.0152. And what is this pressure? 17.5, and this pressure 15 megapascal. So our desired pressure is between, so P at this volume, and what is given, volumes are given. So this is the unknown pressure at this volume, and this is the known pressure at this volume, this one from that steam table, and this is the known pressure at this volume, which is 17.5, and this is the known pressure at this volume, which is 15 megapascal. And X values are the known values. X is the volume, V2, at which we want to calculate this P. And corresponding to this pressure, this is the volume. Corresponding to this pressure, which is 17.5, this is the volume. Corresponding to this pressure, this is the volume. So here we have P unknown minus 15 megapascal divided by 17.5 megapascal minus 15 megapascal is equal to all the volumes. So only unknown is this pressure at this volume. So that comes out to be 15.36 megapascal. So now we have calculated both part A and B using superheated steam table. Before we have calculated both part A and B, V1 and P2 using compressibility chart. Now we have the same V1 and P2, here it should be P2, using superheated steam table. Now we need to find out the percentage error between these two volumes, which we have calculated using compressibility chart and from the steam table, and similarly the error between the pressures, which we have P2, which we have calculated using compressibility chart and also using steam table. So the same equation, sorry. some it is not calculated here. I forgot to make a slide, or it is somewhere misplaced. So you can calculate the percentage error between this value and the V1. This is the V1 which we have calculated using steam table, and we also calculated V1 using compressibility chart, means Z chart, and then we can find out percentage error between these two values. And what is the formula for calculating percentage error is V1 calculated. Which one? This one is V1 calculated, and this one is the V1 actual, because it is from steam table. So V1 calculated minus V1 actual divided by V1 actual. This will give us the percentage error. Similarly here for P2, which we have now estimated from steam table, and we also had P2 from compressibility chart, means Z chart. So this P2 minus this P2 calculated divided by P2 actual. P2 calculated, this is P2 actual divided by P2 actual multiplied by 100%. So then you can calculate the percentage error for both cases, because we need to compare the, actually we do not necessarily need to calculate the percentage error, we just need to compare. Part C is saying compare the results of part A and B with the values obtained from superheated steam table. Okay, so that's all.